Welcome to Lecture 23A, entitled Divergence Theorem in 3D. And this is a tooling example. We just go through a typical example, just sort of make sure we understand the actual divergence theorem in terms of computation on the left side and the right side. The material for this lecture comes from Reading Assignment 4, Section 4.1.1. And the objectives are to develop the skills for applying the divergence theorem to geometrical problems. So you're given a shape and we're going to basically apply the divergence theorem. The concepts, conventions, visualization skills are the closed surface encloses a volume. This is what the divergence theorem basically is stating. And the surface area vector points outwards from the surface that's enclosing the volume.
As usual, the second slide is basically just an outline of the topics to be covered in this particular lecture. And so you can see that our focus here is on the divergence theorem. So this is what we call a tooling example. And there's a certain procedure that we follow and go through it step by step, and then with an example problem to follow.
All right, so let's start now looking at some examples applying the divergence theorem. I call them tooling examples, just so you understand the calculation procedure. And there's a little demo on the side that you can look at and play with it to sort of understand how it can be utilized. And so the problem statement is to compute the left-hand side and right-hand side of the divergence theorem for the pure rotational field. And the rotational this field in this case is given as shown. Rotational field, we know that divergence must be equal to 0. And you're given the surface being two surfaces which have been stitched together. First surface being S1, which is a hemisphere. And the hemisphere basically is given by x squared plus y squared plus z squared equals a squared. Z is greater than or equal to 0. In this example, a equals 2. So that's the radius of the hemisphere. And S2 is the base or the disk of radius A in the xy plane. And that's x squared plus y squared less than or equal to a squared. Z equals 0 being the xy plane. And again, the radius will be a equals 2. So we have these two distinct surfaces, which when put together produce a closed surface. And so what we want to do is to compute closed surface integral of f dot n s ds. And given that the surface is not a continuous surface, we have to break it up into two separate surfaces. We'll call that the left-hand side. There's the integral of the flux, at least the flux calculated over the hemisphere, and the flux calculated over the planar disk. And that is equivalent to taking the divergence of the vector field, which is a scalar function, and integrating it over the volume enclosed by the hemisphere and the planar disk. That will be the calculation performed on the right-hand side. So again, D basically just means the volume enclosed by S. This is the way we should look at these things. All right, so the first step is to compute the left-hand side. And so we will basically look at, first of all, surface S2, which is the circular base. And here it's convenient to use the explicit representation of the surface S2. So first step is to calculate the flux from the circular base. And so that basically is the expression you see here, which is the dot product in the field evaluated at z equals 0 times the differential surface area, dot product of the differential surface area integrated over the area of the circular base. So z is equal to 0. That's the description of the xy plane, that is the circular base. And so since we have an explicit form, the differential surface area vector would be just tx cross ty dy dx. And we can write this out in a general formula form in this form. So this is the minus the partial derivative of z with respect to x minus partial derivative of z with respect to y, 1. Since z is equal to 0, both of these partial derivatives are 0, and you end up with 0, 0, 1 dy dx. And this would be a vector pointing upwards. However, because of the divergence theorem's convention, that means the area vector should be always pointing outwards from the surface, which means downward in this case. We basically have to multiply this through by -1. And so the appropriate differential surface area vector direction to take is the one that's shown here, which is 0, 0, minus 1, and dy dx. All right, so we are now basically ready to do the calculation of the flux. The bounds on the region are shown here. This is the bounds on y. This is sort of a half circle. This is a lower half circle between limits minus a and a. So this maps out the domain of a circle on the z equals 0 plane. This field would have had a z component, but since z is equal to 0, we only end up with x here rather than x minus z. And so we compute the dot product to find an expression that's shown here. This is minus y dy dx. And then this integration can be done, first of all, by integrating with respect to the inner integral, and then finally the outer integral. It turns out for this particular calculation, the resultant value is equal to 0. All right, so now let's do the hemispherical surface. We compute the flux from the hemispherical surface. In this case, it's easier to work with a parameterized representation. And so you can set this up more or less as a problem in spherical coordinates, but the radius is fixed, the radius a being equal to 2. And so you can see here, these are typically the values, the functional description that we would expect if we were dealing with spherical coordinates, but a is a constant in this case. Now, because it's a hemisphere, u is only going to extend to pi over 2 rather than to pi, whereas v will go the full circle. That's from 0 all the way to 2 pi. So this is a description of the hemispherical surface. The next step would be to compute the t partial u and t partial v. If you do this calculation, you end up with this vector. If you do the partial with respect to v, you end up with this vector. And the next step is to take the cross product of these two vectors, and that means you take the determinant of this matrix. Recall, first row are the unit vectors, second row is the first vector, and the third row is the second vector. If you do this calculation, you end up with this result. Now, in this case, the vector is pointing outwards from the hemispherical surface, and therefore it's in agreement with the convention. So we can make use of that now in terms of computing the flux. Again, recall that F has this form, and so now we have to replace y's, x's, and z's with the parameterized values of x, y, and z, which are obtained right here. So this is the x value that we use when we make a substitution. So y value we use when we make a substitution, and this is the z value we use making a substitution. And so all of those are then substituted into here to basically form this expression here. And now we just need to take the dot product of this vector with tu cross tv, which is this one that you see here, integrate with respect to du dv. Well, if you take this dot product, you'll find you'll end up with a value of 0, so no need to integrate because you know the result is going to be to 0 anyways. All right, so now we end up with completing the left-hand side. We've computed this one. We've computed this one. We know this is a 0, this is a 0, add them together and we get 0. So the total flux from that closed surface is 0. All right, we now want to prove that, in fact, the divergence theorem is correct. So let's go ahead and compute the right-hand side of the divergence theorem, which means we need to take the divergence of the vector field F and then integrate over the volume that's between the hemisphere and the circular disk in the xy plane. All right, so here's the divergence calculation. Divergence would be d partial x of the x component, d partial y of the y component, d partial z over the z component. But this term will be 0, this term will be 0, and this term will be 0, so the integrand is 0. I set this integral up just for sake of argument, and so if we're dealing with a hemisphere, that means the z will be from the xy plane to the upper portion of the sphere. That's the hemisphere. This would be basically the bounds of the circular region. That's one half circle. This is the lower half circle, and then the x limits between a and minus a. Well, thank God we didn't have to do this calculation. We could have, because in this case it wouldn't be necessary since the integrand was 0, and so the result is 0. Hence, we conclude left hand and right hand side are in agreement, which they ought to be. Otherwise, we would figure that there's something wrong with the divergence theorem, or we made a mistake. Okay, so now let's look at an example problem. Here's the problem statement. The vector field has this form, and we're interested in finding the outward flux of F across the surface S, which is the surface of the solid bounded by the cylinder x squared plus y squared equals 1, which is this blue region that extends to infinity, but it's cut off by two planes. One at z equals x plus 2, which is up here, and one at z equals 0, which is the xy plane. Now you have two ways of solving the divergence theorem. You can either solve the closed surface integral problem. In this case, there are three discrete surfaces, one for the base, one for the outside periphery, and one for this slanted plane. Or you can solve the enclosed volume integral, which means we need the divergence of the vector field, and then we would integrate the resultant scalar function over the volume enclosed by these three surfaces. Turns out one of these is usually the easier one of the two, and so the idea here is always to pick the easy one. In fact, the problem will be stated in such a way it will be obvious that one way is the right way to go and the other one is just going to give you nothing but grief. Okay, so you'll have to make that judgment. All right, so we can do the solution now. So we can easily show that the planes z equals x plus 2 and z equals 0 intersect the cylinder defined by x squared plus y squared equals 1. So z equals x plus 2 is the top surface, z equals 0 is the bottom surface of solid. All right, so let V be the region bounded by that surface comprised of three discrete surfaces. Then according to the divergence theorem, the total flux basically can be expressed either as a closed surface integral or an integral over a volume which is bounded by, in this case, the three surfaces. All right, so let's basically now compute the flux using the left-hand side. And so since the divergence theorem basically implies the use of a closed surface integral, that is calculating the total flux on the closed surface. In this case, the field is given, just as a reminder, as by this expression shown here. Now, because the surface is not, exterior surface is not smooth, we have to divide this closed surface integral into three separate surfaces, one corresponding to the exterior surface, which is that of a cylinder, the bottom surface, which is a plane, and the top surface, which is an inclined plane. So this would be, for instance, the plane z equals 0, and this is the plane z equals x plus 2. And so each one of these integrals has to be done individually. These, of course, are open surfaces, hence no closed circle around the double integral sign. Also recall that the normal vectors for each surface need to be pointing outwards with respect to the closed surface. Again, that is the convention to be applied when using the divergence theorem. Now for the top and bottom surface, we can use explicit form of surface parameterization. Why? Because z is given as a function of x or y. In this case, z equals 0 and z equals x plus 2. So we'll basically proceed in computing what n valued at z equals 0 ds is and what n at z equals x plus 2 ds should be. We use the general formulation explicit form. This is just minus the partial z with respect to x minus z partial with respect to y, 1 dy dx. If we take this with respect to the plane z equals x plus 2, then we end up with this expression here after having taken the partial derivatives. For the plane for z equals 0, again, similarly, we have zx, zy, but in this case minus 1. Why? Because the vector has to be pointing downwards from the surface. So here it was minus 1. If we multiply this expression by minus 1, then this becomes a positive, this becomes negative. So this is consistent with the convention, and that is on the bottom surfaces pointing downwards. Again, if we take the partial of z with respect to x and y, for the case z equals 0, we end up with 0 and a 0 and a minus 1. All right, so now we have the differential surface area vectors for these two flux contributions. And so for the case z equals 0, we need to substitute in here for the case z equals 0. And so we're left with a vector with x component x to the power 4 and y and z components both being 0. And 0, 0 minus 1, this dot product has to be computed, and this is integrated over the region, which of the circular disk. For the top surface, basically, again, we have the circular disk. But in this case, it's z is equal to x plus 2, so we have to substitute in here z equals x plus 2. And as a result, we end up basically, and z here as well, x plus 2, which is this one here. And then just basically carry out the dot product, and then this can be simplified into expression. Anyway, so next slide. Okay, so let's look at the last surface, which is the outer cylinder. In this case, it's better to use surface parameterization. It's easier. So here we have the surface parameterization, cos theta, sine theta, v cos theta plus 2. And v can range from 0 to 1. So this more or less allows us just to frame the outer cylinder. And of course, it'll have sort of a cut in it, and that's indicated here in terms of the z dependency. That's why this has a v in here, a v cos theta plus 2. All right. Okay, so for the cylindrical surface then, we would just basically compute t theta cross tv, dv d theta. And so the t theta cross tv, you can go through that computation. You'll end up basically with an expression that looks like this. At this point, I leave some of these detailed calculations to you to convince yourself that this is what you end up with. You can also confirm that this vector is pointing outwards from the cylinder surface, which it should be. And now we basically recall from the fact that the vector field has this form. We now basically make the substitutions for x's, y's, and z's. This is the value that's substituted for x, this is the value substitute for y, and this is the value that gets substituted for z. And so this is really all we're going to be doing, converting f now in terms of functions of theta and of functions of v. And so there it is in full form. So now we take this and substitute here. We have the differential surface for the cylinder, which we computed from here. And we take the dot product and put it together. Okay, so that will be the third flux contribution. Now, when you look at all of this, you realize there's a lot of work involved, and some of these functions may be complicated. So I'm going to stop there because the whole point of this exercise was to show you that at some point you have to make the decision, do I really want to do it? Or do I move on and say, let's see if it's easier to compute the right-hand side, which involves integrating over a volume enclosed by these three surfaces. So that's why we move in that direction. Okay, so right-hand side, this is the divergence of the field, dv, integrated over the volume, which basically is enclosed by the three surfaces. So let's do the divergence of f. It'll be just partial with respect to x, partial with respect to y, that's the y component, partial with respect to z, the z component. If you take these derivatives, you end up with this expression here. All right, so this is the part now that represents divergence. It gets substituted in. You have dz, dy, dx. The upper surface, that's the slanted surface, is x plus 2. The lower surface is the xy plane. And this is the region. Okay, this is the projection. So this is a circle of radius 1, upper half circle, lower half circle, and between x of -1 to +1. All right, so this is a simple integral. But it's easier if we do it in cylindrical coordinates. So that means x equals r cos theta, y equals r sine theta, and z just remains as z. That means dz, dy, dx, replaced by the Jacobian and variables used in cylindrical coordinates. And so that's where you see here dz, r, dr, d theta. And this term basically here just becomes r squared. This becomes r cos theta. And so those two combined give you 4r cubed cos theta. And the r remains here. And so now basically you do the integration first with respect to z, which takes you down, basically gives you a function that looks like this, and then you have just a double integral to perform, and this gives you an answer of 2/3 pi. So it's clear that this was just a couple of lines of calculations, and it was much, much easier to perform than had we done the calculation on the left-hand side. Well, that concludes Lecture 23A. Thank you for listening.